Hello everyone, let's take a look at our next problem. An infinitely large floor is tiled with regular hexagonal tiles of side L. Different colors of tiles are used so that no two tiles of the same color touch. A hoop of diameter D is thrown onto the tiles. What is the chance of the hoop enclosing more than one color? Okay, so this is the same as the previous problem, except we're tiled with hexagons instead of squares. And if no two adjacent tiles are the same color, then it really is the same question. We're asking for the probability that the hoop touches more than one tile. Okay. So yeah, this is going to be about areas. This is just going to be computing some areas again, right? If this is L, then we'll say that we can basically say that we're looking at one hexagon and the center of the hoop is randomly distributed uniformly throughout the hexagon. And then we need to look at the area of the subset where the center is allowed to lie. I mean, again, in my mind, I think it's just easier to conceptualize the opposite of what we're being asked for, to first compute the probability that the hoop lands fully inside the hexagon rather than touching the edge. And then we'll just take 1 minus that probability. So as long as we are a distance, if r is the radius of our hoop, as long as we're a distance of r away from the edge everywhere, this will work. It's going to be a little more complicated getting around the corners here. Let me think. Right, I do not want to compute. I don't want to go from a corner out. I want to go a distance of r that way, but also a distance of r that way. Let me think. Let me also draw a bigger picture. Close enough. So we're going to have, there's going to be a hexagon. I'm sure it'll be a hexagon in here that we need to compute the area of, where the distance, all these distances are equal to r. And that's L. So what's an easy way to compute the size of this inner hexagon? I think what I've got drawn here will more or less do what I want. Okay, so that's, if I call that x, then this is also x here. That's 90 degrees. And this hypotenuse of this triangle here, this is L, length, side length of the hexagon. What is this angle of the hexagon? Let me think. Okay, well, let's do a little other impromptu geometry here. That's theta. Theta is equal to 60 degrees because it's 6 turns of 60 degrees to get all the way around. So that means beta is 120 degrees. And this is also beta here. So that means this, in fact, is theta. So the angle here, well, I guess, theta would be enough, right? Theta. So what's the relationship between L and X? X over L is equal to sine theta. So X over L is sine of 2 pi over 6, right? Or pi over 3. Pi over 3. I don't remember what that is, but we'll figure that out later. Okay, so sine pi over 3. So X is then L times sine pi over 3. And let's call this length y. Then I have y is equal to x minus r. R is supposedly given. Well, we know the diameter of the hoop, so we know the radius, of course. So everything here, we have y now. We have y in terms of the two parameters involved in the problem, L and R. Okay. Now, how do I use y to compute the area of this inner hexagon? Well, I can do something similar. I suppose the side length of this hexagon, let's call this S. The relationship between y and S is going to be the same as the relationship between X and L. So y over S is equal to sine pi over 3. So S is equal to y over sine pi over 3. Okay. And the inner hexagon is created from 6 equilateral triangles of side length S. So I need, in fact, and this perpendicular that I've dropped there, that is also of length y. So what is the area of one of these equilateral triangles? Area of one of these triangles is going to be the base times the height over 2, which is sy over 2. And so the area of the hexagon is 3s times y. Okay, so the area of my hexagon is 3y squared over sine pi over 3. And I had y before. Y is x minus r. 3x minus r squared divided by sine pi over 3. Well, let's write this as x is L sine pi over 3. L sine pi over 3 minus r squared divided by sine pi over 3. And if I expand this, I get L squared sine squared pi over 3 minus 2RL sine pi over 3 plus R squared. Okay, so my area of the hexagon, finally, 3L squared sine pi over 3 minus 6RL plus 3R squared divided by sine pi over 3. Okay. So that's the area of the hexagon, of the small hexagon. The area of the large hexagon, in fact, to make this clear, I'll replace the capital H here with a lowercase h to indicate it's the area of the small hexagon. Oops. So the area of the large hexagon, again, the large hexagon is going to be made of 6 equilateral triangles of side length L. Each of these equilateral triangles has a base of L and what is the height going to be? The height is x, right? So the area of the large one is going to be the base times the height over 2 times 6. So we'll just replace that with a 3. And so the probability of landing inside is going to be the ratio of these two things. 3L squared sine pi over 3 minus 6RL plus 3R squared divided by sine pi over 3 divided by 3L. I had an expression for x, didn't I? X is L times sine pi over 3. Okay, so pi is equal to, I'm missing an L here, I'll just put it squared. Okay, kind of like the chessboard version of the problem, we get a cancellation, or that turns into 1 completely. Minus 2R divided by sine pi over 3. And there's an L missing. Plus R squared over L squared sine pi over 3. This looks like something squared, doesn't it? This is 1 minus R over L sine pi over 3 squared. Okay, and so the probability of our hoop touching two colors is 1 minus the probability of landing inside. I guess I'll use this expression here for that. So it's 2R over L sine pi over 3 minus R squared over L squared sine, I'm missing a squared on this, sine squared pi over 3. Let's do a quick sanity check. When R is 0, this is 0, which makes sense because an infinitely small hoop will never touch two colors. And if R is equal to, what is the bound on the radius this time? If I go up to my figure, we should be able to figure this out. Yeah, so if the radius is equal to, if the radius is equal to this distance, then we have a probability of 1 of hitting 2 colors, and that distance is in fact x, which is L times sine pi over 3. So the upper bound is r. The upper bound on r is this quantity, L times sine pi over 3, and you can see if r is equal to that, then this reduces to 1. So that makes sense. I guess the only thing that's left to do is figure out exactly what the numerical value of that is, sine pi over 3. I don't remember my trig ratios here. To be honest, I don't feel like it's terribly important that we get the exact numerical value of that, but I don't know. There's square roots of 2 or 3 or something like that in there. What is it root 3 over 2? Left is an exercise to the viewer. Figure out what that number is. But the approach here was basically the same as the last one, right? Translating the problem into something purely geometric about areas. Computing the areas of these 2 hexagons was a little bit more tedious, but we got there in the end. Thanks for watching.